So now we're going to look at atomic orbitals. And we talked about the wave functions that define these orbitals, and we looked at some examples of formulas that give us a particular shape. And what has happened is we've done calculations and had solutions to the Schrodinger equation, these wave functions, and their mathematical shape defines a specific volume. It defines a shape. And we're not going to worry about what the mathematical equation looks like. What we're going to worry about is what does that shape look like? And it's that shape that we're calling an atomic orbital. And so these are orbitals that are in the atom, and these are where we are likely to find an electron. And so it's not 100% guaranteed, but there's a very high probability, and it actually ends up being about 90% of the electron density is found in these shapes defined by, or in these regions defined by orbitals. Now we are describing these as shapes, and we'll actually draw them out on paper, but just like atoms, there are no specific walls to the atoms. When we think of, say, a cell, a blood cell, there's clearly a cell membrane. When we look at atoms, there's no wall that says here's where the atom stops, here's where the rest of the world begins. Atomic orbitals are the same way. We have some shape where we're likely to find an electron, but there's no wall that contains that electron. It's just the shape itself. So the first one we look at is the s orbital. And in every energy level, so every principal quantum number level, there is a single s orbital there. And anytime L is equal to 0, we are going to have the s orbital. And the s orbital has a spherical shape that's centered around the nucleus. So you can imagine the nucleus right here in the middle where all the axes cross one another. Now, when L equals 0, remember the only possible value of m sub L is equal to 0, and that relates back to the fact that we have a single s orbital and we have a single m sub L value. Now, the size of this orbital is proportional to the value of the principal quantum number n. So the smallest s orbital will be for n equals 1. As we go to n equals 2, the size of the orbital will get larger. It will still be a spherical shape. It will still be centered around the nucleus, but it will be a larger sphere. And again, we draw this as if it has well-defined borders and there's some kind of containment to hold those electrons there. But we're just talking about this region defined by this mathematical function. The next one we look at is the p orbital. Now, remember that L equals 1 indicates we're talking about a p orbital. If L equals 1, we have 3 m sub L values, minus 1, 0, and 1, and that corresponds to having 3 p orbitals. All of these orbitals are of the same energy, and we call that degenerate because they have the same amount of energy. Notice that when we look at the designations on each of these orbitals, we have p minus 1, p0, and p1. These are also sometimes called px, py, and pz. And this is when we were talking about the orientation that the m sub L values indicated. Now that we have 3 m sub L values, there's an orientation to these orbitals. So they're kind of dumbbell shaped, and we actually have this little region at the middle where there is no electron density. And so we have these 3 orbitals pointing in 3 different directions. Now, the designations of these as minus 1, 0, and 1, or as x, y, and z is completely arbitrary. There's nothing inherent about m sub L equal to minus 1 has to correspond to px or anything like that. They're all equivalent energy. It doesn't matter which one we label as which. The same thing also holds true for the size of these p orbitals. As the value of n gets larger, the size of the p orbitals will also get larger. So they will still have the same shape, they will still be centered around the nucleus of the atom, but they will be larger, and so the electrons basically have more volume, a larger region of space around the nucleus where they can be and still be in that p orbital. Moving on to our d orbitals, so that's associated with L equals 2. We have 5 m sub L values when d equals 2, and we also see that we have 5 d orbitals. What we have here for 4 of these 5 d orbitals is they're actually look like kind of a double dumbbell, so it looks like two p orbitals overlapping. And so we see designations here of D minus 2, minus 1, 0, 1, and 2. These also have other designations of X, Y, Y, Z, Z squared, and so some various things. We're not worried about those specific labels. What we're worried about is that there are 5D orbitals and that they are also degenerate. That means they are all the same energy, and this is going to become important when we start to look at electron configurations. Now notice that one of our d orbitals looks a little different. It looks like we have a p orbital, so we see the dumbbell kind of shape on top and bottom, but then we also have this kind of donut-shaped region also centered around the nucleus. What you should be able to do is not necessarily designate, oh, this is dxy, but you should be able to say that recognize that any of these are d orbitals. We also see that as n gets bigger, the size of these orbitals gets larger, and so we have a larger volume centered around the nucleus where we're likely to find the electrons. Lastly, we look at the f orbital. So when L equals 3, that's associated with f orbitals. M sub L has 7 values, so we have minus 3, minus 2, minus 1, 0, 1, 2, and 3. There are 7 values, and that corresponds to the 7 f orbitals. Notice that the shape here gets a little more complicated. Now we have multiple lobes around the nucleus of the atom. We also have some that have a little bit different shape here. So we have something that looks similar to the 1d orbital, but now we have this double donut shape around it. And again, you're not going to have to designate one of these as the specific f orbital. It's just recognizing that these are the f orbitals. So you should be able to recognize them by shape. We also see that as n gets bigger, our f orbitals are also going to get larger. Now we can look at the shapes for orbitals such as the G and H. We're not going to see those because our current periodic table, the elements we know, does not go beyond the f orbitals. However, we can find pictures online that show us the G and H orbitals. So you should be able to recognize each of these types of orbitals by picture. Know which L values designate which type of orbital, S, P, D, or F. Know the number of each type of orbital based on the number of M sub L values. And know that as the n value increases, as the principal quantum number increases, the size of each type of orbital is going to get larger.